Thank you. So yeah, this joint work with Elchanan, Mossel, and Neeman. So this is a talk about property testing, as were the previous talks. So we're interested in the problem of Junta testing. So in particular, we're interested in Boolean functions, so functions which take plus minus one value on the discrete cube. And the function f is said to be a k-Junta if it just depends on some k of the coordinates. Okay? And think of k as constant, let's say 5. Okay? So the motivation of studying Juntas comes from various sources in theoretical computer science. For example, you can think of it as modeling feature selection problems. If f represents some output of a machine learning model, then you can think of a function which just depends on few of the features, even though there are n ambient features where n is very large. I guess the original motivation comes from PCPs and hardness of approximation. And in social choice theory, such functions represent voting functions which depend on only a few voters. So they've been studied from various aspects, and the problem we are interested in is that of property testing. So usual model of property testing, there is an algorithm which has black box access to a function f. It can query it at any point. And the problem of property testing of Junta would mean that the algorithm makes calls to this oracle for f at t points, let's say x1 to xt. These points will typically be randomized. And the goal is that if the function f, the unknown function f, is a k-Junta, then the algorithm would like to output yes with high probability, let's say at least 2/3. And if the function f is epsilon far from every k-Junta g, where the distance between two functions is measured as the fraction of points on the cube where f and g differ. So if f is epsilon far from every k-Junta g, then the function algorithm should output no with high probability, let's say 2/3. Now, the property testing of Junta, this problem has been studied a lot in TCS. There's a partial list of works. And maybe the thing I would like to really focus on, and thing I want you to remember, is that this property can be tested with order tilde k queries, so about k log k queries. But the main feature is that the query complexity is completely independent of the ambient dimension n. Okay? You can test this property without any dependence. Now, what we are interested in is a robust version of this property. So the previous result that I mentioned, all the results I mentioned, most of the results I mentioned in the last slide, in the yes case, you assume that the function is a k-Junta, whereas in the no case, you assume that the function is, let's say, at least 0.1 far from every k-Junta. Okay? So in the previous slide, when I said it's order tilde k queries, I was thinking of epsilon as a fixed constant, say 0.1. And we are interested in the noise-tolerant version of this question. Namely, we want to distinguish between functions, let's say, which are eta, let's say 0.2 close to some k-Junta, versus functions f which are eta plus epsilon, let's say 0.3 far from every k-Junta. So what we're losing, what the difference is compared to the previous case, is that in the yes case, the function isn't exactly a k-Junta, but just close to some k-Junta. Or equivalently, one can put this problem, equivalently another task you can think about is that given oracle access to a function f, you would like to compute the distance of this function to the closest k-Junta g, and you don't need to compute the distance exactly, but just up to some additive error plus minus epsilon as g ranges of all k-Juntas. And you can easily see that task 3 accomplishes task 2. So there has been investigations on the people, this problem has been studied, and the previous best result in this direction is this result of Blay et al., which gives an exponential in k times and polynomial in 1 over epsilon query tester, which can distinguish between functions f which are epsilon over 16 close to some k-Junta versus functions f which are at least epsilon far from every k-Junta. So like all the results I mentioned in the previous slide, the query complexity is independent of dimension n. So for example, it can distinguish between functions f which are 0.01 close to some k-Junta versus functions which are at least 0.16 far from every k-Junta. On the other hand, you can see just because this epsilon over 16 versus epsilon, this result cannot distinguish between functions which are 0.1 close to some k-Junta versus 0.15 far from some k-Junta. from every k junta. So the gap has to be at least 16 times somehow. And in the lower bound side, a result of Levy and Weingarten shows that this problem of tolerant junta testing is asymptotically at least somewhat more difficult than the vanilla junta testing problem. I'll not mention the specific quantitative version of the results. So our main theorem is the following, namely that there is an algorithm which, given oracle access to a Boolean function f and an error parameter epsilon greater than 0, it will make 2 to the k times poly 1 over epsilon queries, again still independent of the ambient dimension n, and it will compute the maximum correlation that f can have with any k junta g up to an additive error epsilon. Since the correlation and the Hamming distance are related by that formula written over there, it means that it solves the problem I first mentioned, namely that it will find out the distance of f from the best k junta possible up to an additive error plus minus epsilon. So in particular, it can distinguish between 0.1 close versus 0.15 far from every k junta. So that's the main result. What's the high-level idea? So at a high level, here's what we want to do. We have oracle access to f. We want to find the best k junta g. We do not know what the best k junta is. Suppose somebody very helpful came along and told us, among the n variables, here is a set S of, let's say, size 2k, maybe the first 2k variables, and it was given the promise that the best k junta g, the k variables in g, it comes from S. Suppose somebody gave me this promise. Well, then the problem becomes easy, as in it can be done with exponential and k query complexity. Why? Well, I can try out all possible choices of k variables from the set S. For each of these choices t, I can find out the correlation, the best correlation that any function f can have with a function dependent just on this set t. The best function which is just dependent on t simply outputs, simply looks at every possible choice, every possible setting of the coordinates in t, and then outputs the sign of the average value that the function f takes on the subcube corresponding to xt. Again, this is not too hard to see. If you look at the best correlation with a function on t, it's the thing I've written in red. Okay, this can be easily checked. And also, this is not the best way to do this, but you can estimate this correlation for every t by just sampling f on, by querying f on 2 to the k times poly 1 over epsilon random points. You can do this. So, okay, if you put all this together, this means that if I give you this helpful set S, you can spend 2 to the k times poly 1 over epsilon queries, and you can find out the best correlation that f can have with the k junta. Of course, all this is not useful for us because we haven't been given any such promise. That we haven't been told what this best set S is. And here's the issue, just to emphasize this point more. The point is that even identity of specifying one variable in the function requires log n bits. And the name of the game here is to have query complexity independent of n. So we cannot know the name of even one interesting variable with order 1 query complexity, where I'm thinking of order 1 meaning that it just depends on k and the parameter epsilon and independent of n. So, okay, this is not going to be useful, but the way we are going to circumvent the barrier is that we are going to use the oracle for f to construct oracles for all the variables appearing in G. So this very closely resembles this testing by implicit learning framework. And then once we have oracles for all the interesting variables, the variables which appear in the best k junta, we will do the same hypothesis testing routine that I mentioned earlier. Okay? Okay, so maybe I should explain what do I mean by constructing an oracle for all the variables appearing in G. Okay. When I say I have constructed an oracle for, let's say, the variable x5, what I mean by this is an oracle which, when you give it any input, let's say 100010, it will output the value of x5. It will output the value of the fifth coordinate. It will not tell me the name of the variable. That's too expensive. That's log n bits. It will just give me the value that x5 takes on this input. Okay? And so we will not know the name of the variable I. And so this is what I mean by oracle for an interesting variable. And once you have these oracles, you can just run the hypothesis testing routine that I mentioned earlier. So, I mean, this should not be unfamiliar. This is very similar to guarantee of list decoding algorithms, local list decoding algorithms, where or local decoding algorithms where you do not necessarily specify the name of the code word. You just you can evaluate it at any given point. Okay, so the thing is, okay, how do we want to construct oracles for all the variables appearing in the best K Junta G, and maybe a few more interesting variables. Maybe we'll construct oracles for poly K variables, okay? And the variables in G will be included in this. How do we identify these interesting variables? How do we identify these variables? And the thing is that we'll identify them by this notion of low degree influence. So so this will require a brief detour into Fourier analysis. Okay, so recall every function on the hypercube admits a multilinear expansion. It can be written as summation f hat s chi s x, where chi s of x is the product for s ranges over all the subsets of 1 to n, and chi s of x is this function, which is the product of all the coordinates appearing in S. And every function can be written as a linear combination of these functions chi s x's. There are 2 to the n such functions. And now the standard notion of degree k influence of a variable I in the function f is the sum of squares of all the Fourier coefficients, all these coefficients f hat square s's, in which I is included in the set S, and the set S is of size no larger than k. That's the standard definition. And now here's the first important lemma. This is not hard to prove. That if you are interested in finding out the best K Junta, which is correlated with G, it suffices up to a plus minus epsilon error. If you're willing to lose an epsilon in correlation, it suffices to just look at the K Junta, which is dependent only on these variables coming from the set capital H. It's a set of variables I which have degree K influence, which is at least epsilon over K squared. It just suffices to look at this. Okay? So you don't need to think about the best K Junta on all these variables. We just need to think about best K Junta on these variables, this calligraphic H. Okay. This is not hard to prove. This is just Cauchy-Schwarz inequality and definition of Fourier coefficients. The 2 important things I would like you to notice is, first, by just, again, definition of Fourier coefficients, it easily follows that the size of this set H is not too large. It's at most poly K over epsilon. So it is not inconceivable that we can construct oracles for all the variables appearing in H. It is a small set. And secondly, even though we are interested in the best K Junta G, that's what we are trying to figure out, the definition of H is just dependent on the function we have at our disposal, namely F. The problem is, again, we have defined this set, but it's not clear how do we access any of the variables in this set. But if we could construct oracles for all the variables appearing in H, we'll just do a hypothesis testing that I mentioned earlier. So now the rest of the task is, how do we construct oracles for all the variables appearing in H? Okay, so here is the high-level strategy. Okay, so I have the function f. Okay, the first thing is, so what do I know about the set H? I know every variable appearing in H has a decently good, which is like some poly epsilon over k, degree k influence. First, I will bring down, by this random restriction idea, will bring down the Fourier mass to level 1. Okay, so here's what we want to do. We have an oracle for f. We will randomly retain each variable, the n variables, independently at random. We will retain each variable with probability 1 over k, and otherwise with equal probability 1 minus 1 over k over 2, we'll set it to plus 1 or minus 1. So random restriction, the usual thing. If you do this, if you do this once, you will get f rho 1. This is the function f obtained after one random restriction. Do this a few times, about poly k over epsilon times. And what one can show, and this is well, I'll tell you how to prove it. It's easy to do it. If you repeat this about poly k over epsilon times, then what is easy to show is that with high probability, think about any particular variable I appearing in H, it will have the property that at least for one of these functions, f rho j, the variable I will satisfy g hat I is at least some poly epsilon over k, where g is some f rho j. So in particular, by doing this random restriction, you will have the property that if a variable earlier had high degree k influence, now in one of the functions in this list, it will have high degree 1 influence. Okay? So do this. Okay, so now I can assume that somehow I have ensured that I have oracle access to a function where an interesting variable I am interested in has large degree 1 influence. Okay? Now what do I, oops. So the way you actually do this is just a careful, it's an easy application of Paley-Zygmunt inequality and just definition of Fourier coefficient, so not very hard. Okay, so at this point we have oracle access to a function g where the variable, any variable I am interested in, or particular variable I am interested in, has decently large correlation with the function, say poly epsilon over k. So I'm calling this variable function g now. This is obtained after one random restriction. Now, but I don't care about just having large correlation with the function that x, my variable has large correlation with g. I want to construct an oracle for the variable xi I'm interested in. And the way we'll do it is we'll use a variant of the usual noise operator. Okay, so this is what we're going to do. Think of a vector eta, which is an n-dimensional vector, each coordinate is 0 to 1. And corresponding to that, think of a product distribution on the cube, or product distribution plus minus 1 to the n, where the ith coordinate has expectation eta. Okay? And now define this operator has eta g of x. Okay? This is an operator. This operator, given a function g, I can define this corresponding function. This is very similar to the function that appears in Husserl's dictatorship test, so hence the name. And this is just a function of x. Okay, you take an expectation over y1 and y2 randomly chosen points from the cube, and you take z, which is drawn from a random sample from the product distribution defined there, and you can define this function, has eta of g. And the nice thing is, if you define this and then do the usual symbol pushing in Fourier analysis, you can show that this operator has a very nice effect on the Fourier spectrum of G, namely the Fourier coefficient corresponding to set S gets hit by eta to the S, where eta to the S is just the product of eta i's, I appearing in S. So it attenuates every Fourier coefficient by this in this very specific way. Okay, I guess I have 2 minutes left or something. Okay, good. So okay. Why are we defining this operator? Okay, so I'm not. At a high level, here is what Fourier noise operators do. Noise operators tend to linearize functions, meaning because as set S grows larger and larger, eta to the S becomes smaller and smaller, right? Think of the case when all the coordinates of eta is 1/2. So it tends to hit Fourier spectrum at a lower level with a much smaller value, with a much larger value than Fourier coefficients at a higher level. Okay, so they tend to in effect linearize functions. But that will happen even if all the coordinates of eta are the same. But if you choose eta carefully, you can do a little more. In particular, here's what you can do. Think of sampling in eta where each coordinate of eta is set to 0 with probability 1 minus tau to the 6. Tau is some poly epsilon over k. And with a very tiny probability, tau to the 6, you set it to tau cube. Okay, this is done with some calculation in hindsight. And then what you can show is that if you start with a g, where g has good correlation with xi, at least tau, again poly over epsilon over k, then with some decent probability, after you apply this operator and do a little bit of manipulation, you can get an oracle for the variable xi you were interested in. Okay, this is not, I went over it very quickly, but the high-level idea is that noise operators linearize functions, but if you use a noise operator where coordinates are chosen carefully, you can in fact not just linearize, but actually get a dictator bit out of it. That's the high-level idea. This is not hard to prove, again. This is just like write down the polynomial, do a little bit of calculation. Okay, so again, maybe just in summary, we were given a function f. You first apply this random restrictions to make sure that you get this poly k over epsilon many different functions, and you have the property that if I was a variable in F with a large low degree k influence, then it will have good correlation, xi will have good correlation with at least one of the functions in the list. And then you apply this Hastert type operator, and if you apply it on each of these functions, you will have at least one of the functions you get at the bottom level, these leaves, will be the dictator function corresponding to xi. That's the whole thing. And once you do this, you can apply the hypothesis testing that I mentioned. The only tiny issue is that you will get all the dictator bits you cared about and maybe some spurious functions, because you are just guaranteed that every variable you cared about will be in this list, but there might be other arbitrary functions. And you can do a cleanup by just applying like one round of dictatorship testing again on top of it. Anyway, I think that's what I wanted to say. Thank you. Yeah. No, the exponential dependence on k, I do not know if it's necessary or not. But here is a problem whose solution is required if you want to go from 2 to the k dependence to poly k dependence. Suppose I give you a function f, okay, on n variables. I give it as a truth table, okay? And I want to know what is there a function on n over 2 bits which has correlation 0.5 with the given function. How many points do I need to query this function f at? I can, of course, query everything, like and query the entire function, then I can find out everything about it. I want to know about the function. Is there anything better one can do? There's no junta part anymore. I have been given the whole function. I want to know how many points you need to query the function to find out the best n over 2 junta.
So the best lower bound is linear?
The best lower bound is, I think, well, I think it's k square or something. Yeah. So here it will be like n square, and the best algorithm is brute force, like 2 to the n. So I don't know what the answer is. Yeah.
Do you need k to be constant, or does it work?
Well, it works for all k, but the point is it will probably be meaningless at some point. So like once k is approaching like n over 10 or something, or whatever be the constants hidden there, it will be meaningless. But yeah.